So let's do the second step, which is, I'll go over that. So the second step is to find the natural solution. We'll draw it for time greater than 0, and we'll plug in these equations. We'll have to determine if our if our circuit is in series or in parallel, and then we'll find our S. So let's go back to our whiteboard. So we're going to draw it for time greater than 0 first. And for time greater than 0, the switch is open. There's no current on our left. There is current flowing through the thing on our right. We're interested in the thing on our right. So we're going to draw our thing on our right. We've got this capacitor. Can't draw it as a voltage source here, because for time greater than 0, it's not a constant 6. It's not a constant voltage source. It's changing around. Oh, but look at this. We can combine our resistors, right? We can combine our resistors and make that look like just a single 9-ohm resistor. And we're still interested in, we still want to find that current. So from the other sheet, we said that the sort of the magic pre-made equations are alpha is equal to R over 2L if it's in series. It's equal to something else if it's not, if it's in parallel, but here it's in series. And so for our equation, that's 9. And omega naught is, regardless if it's in series or parallel, always equal to 1 over the square root of LC, which for this equation, for this circuit, is 10. And S is always equal to minus alpha plus or minus the square root of alpha squared minus omega naught squared, which here is equal to minus 9 plus or minus J, 4.36. And the first number is alpha. Whoops. It's almost correct, but not quite. The first number, not including the minus sign, is alpha. And the second number, which is always taken to be positive, is omega sub D. Your alpha is always going to be positive if you have a stable circuit, which all of our circuits are. So your alpha will always be the positive part of the first number, of the real part, and your omega sub D will always be the positive part of your imaginary number. So now we've got 3 different numbers. Our alpha here and also down here will always be the same. Our omega sub naught and our omega sub D. And we've got to determine which case we fall into. The relative strengths of our desire to, of the strength of it decaying to the relative desire of it to oscillate, which is omega naught. And for this particular case, we see that 9 is less than 10. So this is the case that we're in. And we're in a underdamped case, which means it's going to oscillate, which means we're going to get sines and cosines in our equation. And so when we look at which one of our magical equations, our pre-solved plug-and-chug equations are for a natural solution. So all of step 2 is finding the natural solution, which, since we want to find current, we'll call I sub n, n for natural. It's going to be of this form. C1 is a unknown coefficient. It's constant. We just don't know what it is. And this is omega sub D, not omega sub T. You'd think that they would give us a different 2 variables that were not so similar than omega sub D and omega sub T. But I'll tell you what they are. Intuitively, alpha is how much the circuit wants to dampen. If alpha is really big, it means your resistor is really, really huge and it takes forever for the circuit to slow down. It's not going to oscillate. if that's the case. Omega sub naught is a measure of how much the circuit wants to oscillate. It's actually the frequency that the circuit would oscillate if the resistor was 0. Omega sub d up here, this is if the circuit does oscillate when it's all put together. In other words, if this case is true and it really does oscillate, what frequency does it oscillate? And that's why it appears down here.